All right, welcome to the afternoon session. Our first speaker is Melanie Weber, who is a professor of applied mathematics, computer science at Harvard and works on geometric machine learning. She's going to tell us about discrete curvature and applications in graph machine learning. So, take it away.
Yeah, thank you. Thank you very much for the introduction and for having me. It's been the talks that I've seen so far has been really great and covering a really broad range of topics. So excited to be here. Yeah, so as was said, my talk will be about graph machine learning and in particular about how we can use tools from discrete geometry, such as discrete curvature that you already see in the title, to design and improve machine learning algorithms. So most of the talk will be fairly methods focused. So there will be few sort of concrete applications that we will see. But I want to start with some concrete examples of how a learning problem in that space might look like, so that you can have that kind of in the back of your mind as we go through and think about the algorithms and the architectures that we're going to introduce. So typically in a graph machine learning problem, our input is either a single graph or a collection of graphs, and typically those are attributed. So we have not only an adjacency given, so we know which node connects to which, but we also have some features associated typically with the nodes, sometimes also with the edges. A classical graph machine learning problem that we often encounter is graph classification. So here our input is a set of graphs, such as in this example, the chemical structure of a set of molecules. And then we want to predict some label, maybe the property of those molecules, such as toxicity or how efficient such a molecule could be in a track. And we want to assign such a label to each graph. Another example, this is now a node level task. So here our input is a single graph, and we want to assign labels to the individual nodes in that graph. An example could be if our data set is a social network and we want to label the nodes, the users in the graph according to whether we think that they're human or they're bots. And then to give you one more example of link prediction, also a node level task. So here we have a set of nodes given and maybe a few edges between them, and then we want to predict additional edges. An example could be in track discovery, for instance, where each node represents a track, and an edge represents an adverse reaction. And there are some adverse reactions that are already known to us, and then maybe we want to predict potential other adverse reactions. So now, of course, these examples are not related to physics. Those are sort of my standard examples that I usually give at the beginning of a talk. I want to point out, though, that a lot of problems in physics and material sciences, so closer to the research area of probably most of the people in the audience, many problems in that space can also be formalized as examples of those kinds of cross-structured learning problems. And I want to just point out one example, a really nice paper by Boris Kosinski's group at Harvard, which I think also involved a few people from IAIFI, Batzner et al., where in that paper, graph neural networks were used to model to understand something about atomic potentials in the context of material discovery. Okay, so with these examples in mind, let's go towards the methods and the mathematical tools that we want to use. So I already said we want to use tools from discrete geometry, in particular discrete curvature. Now, curvature classically is a tool from differential geometry, and oftentimes when we think about curvature, we associate that with continuous spaces, with surfaces, for instance, right? So even if you haven't taken a course on differential geometry, you probably know that the Euclidean plane, for instance, that you see here, that's a flat space, so it has curvature 0. The sphere is an example of a positively curved space, has curvature equal to 1. And then the satellite structure that you see on the right-hand side, that's an example of a negatively curved manifold. Now, here we are in a discrete setting, so we need notions of curvature that can be defined on discrete data structures, such as graphs in our case, but more generally, the hypergraphs, simplicial complexes, polyhedral complexes, point clouds, and so forth. So we want to talk in a bit how to define such notions on discrete spaces. and we will use curvature analogies. So typically it's not possible to define one-to-one analog of the classical curvature notions in the discrete space, in particular because we tend to not have a differential structure. But we can often say that there are certain properties, certain geometric properties that are characterized by curvature and that have a good analog in the discrete setting. And then using those relationships between curvature and other geometric tools, we can find or define good, meaningful notions of curvature in the discrete setting. And we will look at two of those. And then once we have defined these curvature notions, we want to talk a bit about how we can use those curvature tools in graph machine learning. And before we go into that, I want to give you sort of some high-level examples of where curvature might be used in graph machine learning, and then later on we will zoom into some of those. So a classical example, and that's in fact one of the earlier algorithms where curvature was used in graph machine learning, is for community detection. So here it's closely related to node classification that we just talked about. So here our input is a graph, and we want to find in an unsupervised way densely connected substructures in the graph. And typically those correspond to nodes that share a certain properties. So for instance, if we think back to our example of social networks, those communities might correspond to people who went to the same school or the same college and are densely connected with each other because they follow each other, they know each other in real life. So oftentimes we're interested in recovering such densely connected substructures, such communities. There are different variants of this problem. Sometimes we're sort of in an easy setting like here where everything is nicely separated. Sometimes these communities are overlapping, but in each of those settings, we can find curvature-based algorithms that use a geometric characterization of the graph that we get from the curvature to recover those communities. If you want to learn more, I put here some references. I will not talk in detail about this application, but just to give that as an example. What we will talk a bit more in detail about in this talk are uses of curvature in the context of graph neural networks. So graph neural networks are a deep learning architecture for graph structured data. It's been used very successfully in many domains, including in the context of these sample problems that we saw earlier. But graph neural networks are not without challenges, and there are certain challenges, limitations that arise during training and related to the kinds of functions, the kinds of learning problems that graph neural networks are good at versus that they're maybe not so good at. And it turns out if we use the geometric structure of the graph and take that into account when we design those algorithms or augment our models, our data with certain geometric information, we can mitigate some of those limitations. And we will see examples of that in the talk. Another example, in many data sets in general, including in graph structure data, we encounter multi-scale structure. And sometimes it's important to encode different structural properties at different scales. So being able to coarsen our graph and analyze it sort of separately at different scales is usually a very helpful tool. Something that we can use sort of standalone in shallow graph learning, but also that we can build into graph neural networks as a pooling layer. And it turns out curvature can be used to design a pooling layer that we can then sort of build into our graph neural networks. That's very recent work. I put a reference here. We won't have time to go through it in detail, but just to give one more example. And then the last example is again something that we will take a closer look in this talk. That zooms out a little bit from just looking at graph structured data, namely looking at graphs that were constructed from point clouds, so graphs that encode some kind of spatial information. And in this setting, it makes sense to ask how those discrete curvatures that we will define on graphs, how they relate to curvature in the continuous setting. And in particular, we can use such tools to learn something about our data manifolds that could then have implications for how we do representation learning or the complexity of certain models, certain deep learning architectures that we use in practice. Okay, so that's the plan for today. Brief introduction of discrete curvatures. Then we want to talk about graph neural networks and how to use curvature there. And then talk about these continuum limits. So what is the relationship between discrete curvature and the classical curvature in the continuous setting? Yeah, so just to recap, we already briefly discussed this. So unfortunately, the classical notions of curvature that we have in the continuous setting do not translate one-to-one to the discrete setting. So we have to rethink a little bit how we define notions of curvature in this discrete setting. The way to go about this usually is to look at curvature analogies. So we know, for instance, in the continuous setting that curvature in this context, by the way, we're looking at Ritchie curvature, which is a local notion of curvature. There are other notions of curvature that one could consider, but in the context here, we're just looking at Ritchie curvature. So we know that Ritchie curvature in the continuous setting relates, for instance, to the behavior of random walks on manifold. It also relates to the Laplacian in those spaces, the Laplace-Beltrami operator. And each of those two geometric tools have analogies that are well described in the discrete setting. So for instance, on graphs, we have the graph Laplacian that sort of takes the place of the Laplace-Beltrami operator. And we can also think about random walks on graphs. And ideas behind the two notions of curvature that we will see in this talk are to take these two connections of curvature and other geometric characteristics and find a notion that's consistent with that in the discrete setting. Of course, that means that some of the other properties, including very helpful properties that curvature might have in the continuous setting, do not translate one-to-one to the discrete setting. But by picking a curvature notion that preserves the kinds of relationships that are important in our setting, in our learning problems, we can sort of mitigate this in practice. So the first notion that we want to look at was introduced by Olivier roughly 20 years ago. This is built on a connection between curvature and the behavior of random walks. Namely, in the continuous setting, we're not going to show this here, but one can show that in the continuous setting, if we start two random walks at nearby points, that they're very likely to draw close together if the manifold is locally positively curved, and they're very likely to draw apart if the manifold is locally negatively curved. So in the discrete setting now, if we look at a graph like the cartoon that we have here, we can simulate a similar setting of random walks by saying we start two random walks at nodes U and B that are adjacent to an edge that we're interested in. And then let's say we just consider uniform random walks. So in that case, each random walk would jump with probability 1/degree to a neighbor in a given step. And then to characterize the behavior of the random walks, we could look at what is the measure that these random walks induce. In that case, it's just a uniform measure, and that's called that MV1 and MV2, so centered at the two nodes. And then if the two random walks stay close by or draw close together, then that would mean that they're exploring a similar region of the graph. Right, and that usually happens if there's a lot of overlap between the two communities. So in this case here, we have one triangle, and if we had a lot more of these triangles, then it would be very likely that the two random walks would stay close together. On the other hand, if the two neighborhoods are very disjoint, then the random walks are very unlikely to stay close by and will sort of proceed into each node's neighborhood and then from there into the network. So in a sense, these measures, or the overlap between those measures, more likely, characterizes something about the density of the graph. So that's something that we will go back to. The overlap between those neighborhoods that's important or tightly connected to the behavior of the random walks, that is something we can measure with the Wasserstein-1 distance between the two measures that are induced. So this is a optimal transport problem, right? We put mass on the neighborhood of one node and then transport that onto the neighborhood of the other node. So that overlap is captured by the W1 distance, and that will be large whenever there's not a lot of overlap, not a lot of triangles in that setting. And it will be small if there's a lot of overlap between the neighborhoods. And then you see what Olivier did there. He just said we define a curvature that is 1 minus normalized version of this distance. And that will be negative whenever the two neighborhoods are very disjoint, so when the marks are likely to draw apart, and it will be positive whenever the neighborhoods are very densely overlapping and the random marks will stay close by. So that's one way to define an analogy to how curvature and random walks connect in the continuous setting in our graph setting here. And then there's a second notion of curvature that I just want to briefly point out here. That works of this connection between Ricci curvature and Laplacians. The derivation is a little bit more involved in the channel setting, or that's a notion of curvature that can be defined in a very general setting. Originally, it was defined on CW complexes, which include graphs as a special case. By using the structure of the graph Laplacian, we can find a curvature notion that preserves this fundamental relationship, the Bochner-Weizenberg identity, in the continuous setting. What's important to note here is that while Olivier curvature is very well studied and sort of easy to connect to the structure of the graph and various other graph characteristics, it's quite expensive to compute, right? We have this Wasserstein-1 distance in the definition, so that means we have to solve an optimal transport problem each time we want to compute the curvature of an edge. And if we're in very large graphs, that's sometimes not possible. So in that case, we have to work with approximations of that curvature or something like Foreman's curvature, even though we didn't discuss it in too much detail. You see here, that's a simple combinatorial notion that aggregates simple information like what are the degrees of the nodes, how many triangles and quadriangles are adjacent. So simple combinatorial information that is aggregated, and that's much easier to, or much more efficiently computable than solving an optimal transport problem. So you will see in a lot of the applications that usually we talk about or motivate this by Olivier's curvature because we understand its relationship to the geometry of the graph better. But then in practice, if you're in a very large scale setting and we need a scalable notion, we might switch to Foreman's curvature. And one can show a lot of relationships between those two curvature, even theoretical results. And usually in practice, we lose a little bit if we move to the Foreman curvature setting, but not too much. It's usually a quite good proxy and gives us the same kind of geometric characterization that we get from Olivier's curvature. Okay, so now let's move on to graph neural networks. And in particular, earlier we discussed various ways of integrating curvature into graph neural networks using curvature. We just want to focus on something called encodings. So just to recap, in case you haven't seen this before, I would imagine most of you have. So most graph neural networks that we use today in graph machine learning are based on the message passing paradigm. Message passing follows a quite simple scheme that I want to just briefly introduce. So in message passing, we learn a representation of each node that we initialize with the features, the attributes that are given at the node level at input. And then in each iteration of message passing, in each layer of the graph neural network, if you like, we aggregate the current representations of a node's neighbors in some way. So using some summary statistics such as averaging or taking a max or something like that. And then we use this summary statistic and the current representation of our node and pass that through an update function, usually something like an MRP, and that gives us an updated representation. So basically what happens over several iterations of message passing is that we learn a joint representation of the information that's given in the adjacency metrics and of the information that's given in the node attributes. And then we use these representations for downstream tasks. So as I said earlier, that's a very popular architecture and in many, many domains and for many graph learning tasks that works really well, but it's not without limitations. In particular, we can show that graph neural networks can't just learn any function. There are in particular like very notable examples of functions that graph neural networks cannot learn. And one way to understand or to analyze what functions of what classes of functions that might be, it's interesting to look into graph isomorphism testing. So graph isomorphism testing means we look at two graphs and their adjacency matrices and attributes, and we want to decide whether or not those two graphs are topologically identical or not. Where topologically identical means that if we were to permutate the rows and columns in the adjacency matrix, we could go from one graph to the next. So basically, after permutation, the two graphs are the same. Now, that's a very important fundamental problem that much predates graph neural networks. And there's a long history of looking into how to perform graph isomorphism testing. We don't have an efficient algorithm for that. We only have heuristics for this problem. And it turns out that one of those heuristics, namely the Weiss-Feiler-Lehmann test, is very closely related to the message passing paradigm. And in fact, we can show that whenever this heuristic, the Weiss-Feiler-Lehmann test, lets us distinguish between two non-isomorphic graphs, then a graph neural network based on message passing can also do that. And if it cannot distinguish two non-isomorphic graphs, then a message passing graph neural network can also not do this. And why is this important in our context? It allows us to understand failure modes of the graph neural network. So for instance, here are a couple of examples of graphs that a graph neural network could not distinguish. So for instance, in the upper row, we see two regular graphs, which are obviously very different graphs, right? The G1 on the left-hand side is a connected graph, G2 is disconnected. The size of the largest cycle is different in both graphs. So those are topologically very much not identical, but a graph neural network would learn exactly the same representations for both graphs. So it would not allow us to distinguish between those two graphs. And then that has implications for certain graph structured functions that we might learn. So for instance, if we rely on properly encoding whether or not the graph is connected or what the largest cycle in that graph is, then those types of functions will not be learnable with a graph neural network. And unfortunately, those kind of failure modes are not restricted to simple examples like regular graphs. What you see in the bottom row is a set of non-regular graphs that a graph neural network could also not learn to distinguish. And those are both chemical structures, right? And if you think back to some of the sample problems that we mentioned, this could be something that you encounter in a real learning problem. So that is really those limitations really can be an issue. So what can we do about this? We could endow the graph neural network with some additional structure, some structure that it cannot learn on its own. And by doing training, the graph neural networks, by giving it this additional information, we can hope that maybe it can learn more meaningful representations that allow us to distinguish a larger set of non-isomorphic graphs and then in turn perform better in a downstream task. Now, there's been several proposals of what kind of structural information could we potentially give to the graph neural network to improve its performance in a downstream task. You see here in this table a couple of proposals that have been made in the literature and that have been used with varying success in practice. So for instance, we could encode information about the spectrum of the graph Laplacian. We could look at what kinds of substructures are in the graph and encode substructure counts. So that's for instance a famous example. Substructure counts is something that the graph neural network cannot do, right? If it can't learn like what the largest cycle of the graph is, it can also not tell us how many cycles of a certain size are in the graph. We could tell it something about the distribution of node degrees in the graph, or and that's our proposal. We could give the network access to a geometric characterization of the graph via curvature. I should note here, so there are sort of two goals that we have when choosing and encoding. We want to give additional information that's really helpful to improve the representations that we learn. So that's helpful in downstream tasks. But at the same time, we still have to train the neural network, right? So we don't want the task of having to compute that information be really expensive. because it's really just a pre-processing routine, some additional information that we augment the graph with, and then use and then use during training. So we don't want this to be extremely expensive. And if you look at the complexity of some of those graph characteristics, let's say the substructure counts, you see that some of those can actually be very expensive, and that can be problematic. So for curvature, some of that we already mentioned earlier. So if you think back to what we said about Olivier's spreadsheet curvature there, that gives us a nice characterization, for instance, of sparse and dense regions in the graph. Curvature is also able to capture multi-scale structure in the graph, and generally is tightly connected to other graph characteristics, so capture some of the same information that's also characterized by other tools and other characteristics. So with that in mind, how do we go about giving the network access to that information? So we look at each node in the graph, and then look at the distribution of the curvature of the adjacent edges, so the curvature in the neighborhood of the node. And then we compute some summary statistics of that. So something like the min and the max curvature. So this, for instance, relates to the density. That's very important information. And then some other summary statistics, such as the mean or the median. Which exact summary statistic you choose is actually it's quite robust to that choice. It's important to capture the min and the max, and then some summary statistic, but not there's some flexibility here. And then those additional values we just attach to the features of that node, so to the attributes that were given at input. And then we train the neural network just as we usually would, using message passing. Olivier's curvature tends to work best for that. It gives us the richest characterization of the geometry of the graph, but we can also use other faster, more scalable notions of curvature to speed up this preprocessing routine and still get good results. So what does that do for us in terms of widening the range of non-isomorphic graphs that we can distinguish? Indeed, it provably extends the set of functions that we can learn. And to illustrate this, I just want to give you one example. Those two graphs here are the Rook and the Chicante graph. Both of those are regular graphs. So this is one example of a failure mode of classical message passing graph neural networks. And what's also interesting about this example is that some of the other encodings that have been proposed unfortunately fail in this case. So both of those graphs have the same spectrum. So the spectral encodings do not really help us. They also, of course, have the same degree distribution, so that also doesn't help us. With the substructures, we have to be very careful with choosing the right substructure. And if we don't hit the right set of substructures, we won't see any benefits. But curvature actually really helps us to distinguish those two graphs. So that's information that allows us that is different between the two graphs. And that has something to do, I won't have time to go in detail, but what you see here in the colors is basically the optimal transport plan to compute the Wasserstein-1 distance for the edge between U and B in red. And you probably can, even by looking briefly at it, spot that those two optimal transport plans are different. So hence we will see a different curvature, and by giving the network access to that curvature information, it can distinguish between the two graphs. And that's also something that we see in practice. So here are some examples for some graph classification and node classification tasks. And you see for different, like each block is a different kind of message passing architecture. And then you see different kinds of encodings. And at the bottom row in each block, that's with the curvature encodings. And you see that we see sometimes quite massive improvements from giving the network access to this geometric characterization via curvature. Okay. And in my last remaining minutes, I just want to very briefly talk about the continuum limits. So now we're slightly switching gears. So most graphs that we see in graph machine learning do not encode spatial information. But suppose we're in a setting where maybe we start with a point cloud. So with some samples that are drawn from some manifold. So we have some points that live in RD. And we want to learn, we just have the point cloud, the samples, and we want to learn something about the geometry of the manifold. So only the points are given to us. We know nothing about the manifold. One thing that we could do, and people have done in manifold learning for many decades, is to construct a similarity graph or an epsilon net from it. So each point in our sample becomes a node in our graph, and then we draw an edge if the two nodes or the coordinates that belong to those points, if based on that, they're within an epsilon distance. So that gives us some kind of graph here, G epsilon, or more likely a whole family of graphs where each graph corresponds to a certain length scale epsilon that we have chosen. So now, if we want to learn something about, recover something about the geometry of the underlying manifold, we could sample more and more points, and then at some point in the continuum limit, we would like more and more closely approximate our underlying manifold. So it's an interesting question to ask, if we have a graph built from a finite sample, what can we learn about those characteristics of the underlying manifold? In the context of curvature, the first natural question to ask is how well the discrete curvature that we would measure on the graph aligns with the local curvature on the manifold, right? So how consistent is this discrete curvature in that setting with the classical Ricci curvature? But perhaps more importantly, we can also ask whether we can learn with this formalism something about global bounds on the curvature of that underlying manifold. And those bounds tend to have a lot of applications in representation learning, also related to complexity type questions. So that is, if we can approximate those bounds well, that is very helpful. Now, curvature has, in this settings, the continuum limits of curvature have been studied only very limited and only under very special assumptions. But for other geometric characteristics, such as geodesic distances, so if we measure distances in our point cloud, we measure distances in the ambient space. But most of the time, what we're actually interested in is understanding the distance between points measured directly on the manifold, right? The geodesic distance. So how well can we recover that from a finite sample? Also, continuum limits of the graph Laplacian have been well studied. So if we compute the graph Laplacian, does that tell us something about the Laplace-Beltrami operator of the underlying manifold? And what we're doing in this work is to think about what we can say about curvature and how, in particular, Olivier's Ricci curvature allows us to learn something about the Ricci curvature. And it turns out we can, in fact, show that Olivier's Ricci curvature computed on a geometric graph allows us to learn at least locally the Ricci curvature, right? And I've written that here a bit informal. There are a few things are hidden in certain variables here. You can make that much more precise. But what you see from this inequality here is that we can like quite precisely say how good that approximation is, right? It's a non-asymptotic result. We can precisely say how good of an approximation can we get with endpoints, and how does that depend, for instance, on the dimension of the manifold. And we can also, important for practice, we can learn something about the global bound on the curvature. And again, here we have a non-asymptotic result. So again, we can say something about, we can give a bound on the error of our approximation with n samples and in the dimension, and then also other dependencies, for instance, how we should choose the length scale to get a good approximation. And let me conclude with just a brief discussion of where these kind of continuum limits can be applied. So first, from a representation learning perspective, understanding something about the geometry of our data has been of great interest for decades, right? Usually we look at the intrinsic dimension of data. So classical manifold learning algorithms like multidimensional scaling or isomap, for instance, focus on that. They do a nonlinear dimensionality reduction and attempt to learn the intrinsic dimension of the data and find a good low dimensional reduction of that data. And then more recently, there's been interest in understanding also something about the curvature of data manifold. For instance, there's this work cited here by Amari and Lefrod that looks at extrinsic curvature. And what this formalism gives here, and we think for the first time, is a way to learn something about the intrinsic curvature directly from the data without having to approximate the second fundamental form, for instance, or other sort of more channel tools that tend to be hard to approximate directly from data. So from a representation learning perspective, if we want to learn something about the geometry of our data, we think this could be a very helpful tool. And that's my last slide. I want to briefly also talk about how this links to the learning complexity of neural networks in deep learning. So now not restricted to graphs, just sort of more channel. And it's an interesting question to ask. So in practice, we know that training neural networks with gradient descent works usually quite well in practice. But from a theoretical perspective, it's interesting to zoom in into that question a bit more and ask whether that's always possible, under what conditions we can efficiently train neural networks. And it turns out that for fully connected shallow neural networks, that is not always possible. So you can construct instances that are not efficiently learnable even under simple data distributions. And that's been shown like in the maybe last 5 years. Now moving to the geometric settings, graph neural networks are one instance. More generally, if we encode symmetries into neural networks, we have equivariant neural networks, right? So one can ask whether encoding this additional geometric structure into our network architectures, whether that removes some of these fundamental limitations regarding efficiently learning, efficiently training neural networks. And unfortunately, it doesn't. It gives us some reduction in the complexity, but not enough to get rid of the fundamental exponential dependency that we have seen in the non-geometric setting. So more recently, what we asked, what about the geometry of the input data itself, of the data manifold from which our input is drawn? And typically what we implicitly assume oftentimes is that we work in the setting of the manifold hypothesis, so that our data is sampled from a low-dimensional manifold, right? And then we can ask, what are properties of that low-dimensional manifold under which neural networks are efficiently trainable? And it turns out that there are conditions that we can find that provably lets us efficiently learn neural networks. And one of those instances, for instance, is to have a bounded Ricci curvature. Right? So you see the connection to the continuum limits. The continuum limits allow us to learn a bound on the Ricci curvature of a manifold directly from data. And that knowledge, one application of that knowledge, for instance, is to tell us whether or not we can, here in a regime where we can efficiently learn a neural network. Related to this question there, I'm just mentioning that here some more open questions. So there are some geometric settings that we can characterize. There are also some settings where we can provably show that you cannot learn neural networks efficiently even under the manifold hypothesis. But there are also some interesting cases that are still open. If you're interested in that, please have a look at the paper. Okay, and with that, I conclude just to acknowledge here the main co-authors and the funding. And here are some references if you want to learn more. Thank you.
We have time for some questions.
Hi, great talk. If I understood your theorem, it's basically saying that this graph approximation of Ricci curvature as epsilon goes to 0 is recovering the right thing. Is there a similar theorem for the spectrum of the Laplacian?
Yes. So
sorry if I missed it.
Actually, that's quite well studied. So I put here just 2 papers, including one from my co-author, Nicolas Garcia-Trias, and there are also some older papers. Yes, there are continuum limits for the spectrum of the graph Laplacian. And they actually have some very interesting implication of things like Laplacian eigenmaps, spectral embeddings. There's some really interesting theory there.
So if I have a physics situation where I in principle would be interested in the spectrum of the Laplacian, but I don't know the metric, I could use this as an approximation technique?
Well, so this is a theoretical result. It just basically guarantees you that if you build your geometric graph in the right way, you learn some sort of approximation. And then our results, and the results that are known for the graph Laplacian, give you sort of a theoretical error bound. Okay, what error you could expect with, like with n data points, for instance.
Thanks, that answers my question.
Other questions? I mean, you should have known you were gonna have a question and set up.
Thank you. I actually have two questions. The first one is essentially towards Jim's question as well. So if you have the ambient space and the manifold that lies inside of it, you said sort of you consider the pullback of the ambient space ambient space metric to the manifold, and then there's a relation to the Olivier curvature, but what fixes the metric you chose in the ambient space? I missed this right sentence.
With that I crossed over due to time limits. So we only assume access to, we are in this setting too. So we only assume access to distances, like pairwise distances between the points in the ambient space. And that's what we construct our graph from. We don't assume access to the geodesic distances. That's one advantages of this setting, and that we can work around this. So we kind of build like a data-driven approximation of those geodesic distances of this correction into the metric that we impose on the graph. So all the details are in the paper if you're interested, but yeah, we thought of that.
Okay, so this then in the end doesn't necessarily give the same as the Olivier or the Forman curvature?
So for Forman curvature, we don't have a result like this, but this is for Olivier's curvature. So the curvature that I introduced earlier and the consistency with Ritchie curvature. Just Ritchie curvature, not the full second fundamental form, just Ritchie curvature.
Okay, thank you. And my second question, to choose a meaningful epsilon, do you consider an epsilon filtration like people do in persistent homology and then sort of freeze it at points where the geometry doesn't change too much, or?
That's a great question. Yeah, epsilon has to be chosen carefully. We don't want it too small and we don't want it too large, right? Otherwise we don't capture meaningful geometric information. So epsilon has to be chosen carefully. And there's a discussion of that in the paper, nothing that I can capture in 2 minutes, but yeah, that's a very important point to choose the next scale carefully.
Thank you.
Other questions? Anyone here in the back while I'm still here? Yes. Thanks, Melanie. How important is it that you have uniform samplings from M? Or if I had some kind of non-trivial density living on M, is there anything that I can do? Do any of these results or methods hold or generalize?
That's a great question. Yeah, so in this paper we assume like uniform sampling. I would suspect that you can probably extend this to other sampling procedures. But I think it would require some work. So those theoretical results, like in practice, it probably like works reasonably well. We only tested it on toy manifolds so far. But yeah, for the theory to hold, we have that uniform sampling assumption, and I think it would require some work to get rid of that. Yeah.
Any last questions? If not, let's thank our speaker again.